and start sharing my screen. And last class we left off discussing symmetry. Before we pick up from there, does anybody want to look at anything from any of the homework or from any of the activities? If I waited long enough, can I go on the assumption that this means right now there are no questions? Um, I was looking this morning, and again, I should have said this earlier, I apologize, at the course schedule and the course syllabus. And I'm looking at the date in the syllabus for the exam for this chapter. So let's add a page here. Chapter 11, the exam date is the 19th. Initially, I was thinking that we would have the test available from the 17th to the 19th, but the 19th is next Friday. Is it easier for you folks if I have an exam open over the weekend than midweek?
Yes.
Yes? Okay, so let's say that the exam will be available from next Friday through Sunday, which would be the 21st, end of the day. Today, I think hopefully we'll finish with new content. So Monday and Wednesday, you know how each chapter we've kind of ended with a couple of wrap-up days, answer question type of days, go over fine detail type of days. But I think next Friday we might start doing the introductory into chapter 12. And so chapter 12, which will start on Friday, the 19th. Before then, you need a straight edge. A straight edge could be an index card. Some people like to use rulers, something to draw a straight line. And you also must have a compass. And a compass, again, is that tool that you use to draw a circle in terms of compasses. The ones that I have look a little bit non-traditional. They, if we were in class, I'd be on campus, I'd be handing out ones like this that look like this for people to borrow. You might have seen ones that look a little bit more like this. This one was a little bit fancier. It was a little bit more expensive. I think I got it on sale for like $5 at office supply store. I like ones where you can lock it so that it doesn't wobble when you draw your circle. But if all you can get is those dollar store compasses, just be careful with it. But for that next unit, you need to have a compass. So by next week, if you don't own a compass, please go out and purchase one. Okay. That having been said, we left off with the idea of something having symmetry, meaning that after a transformation, it lands on itself. It looks the same. It's its own image. We talked about line symmetry, being lines that we could fold our diagram over and have it land on itself. We talked about rotational symmetry, something like we can turn it to a separate angle and it looks the same. We had said that if we had something like an equilateral triangle or a regular polygon, they will have that rotational symmetry because when I turn through whatever that central angle is, it'll look the same. We talked about point symmetry, saying that there's a point in the middle of the figure where if I go the same distance away along a straight line on either side of that point, I should be taken back to my original figure. We said the easiest way to tell if something has point symmetry, we can turn it upside down because point symmetry is equivalent to 180-degree rotational symmetry. Everybody okay with those different types of symmetry?
Yeah.
Okay. Then the next is translational symmetry. And translational symmetry means that if I can slide and have the figure end on itself. And in this section of the textbook, the author spends a bit of time talking about different types of rotations, and of all things, things like wallpaper and wallpaper borders. They have their own symbolism and notation that they use for different symmetries in wallpaper. I don't think we need to go into wallpaper at such a great detail, but is everybody in the room familiar with wallpaper? Has everybody seen a room with wallpaper? Has anybody ever hung wallpaper?
No.
No? Well, when you hang wallpaper, with wallpaper, there's a repeat. And so when I wallpapered my bathroom several years ago, you want to make sure that when you where there's a seam, the two sides of the pattern match, and the pattern repeats every so frequently. And so if I were to have like a strip of wallpaper, I'm going to say that the ends are broken, it might have this pattern that repeats. And so every time I shift over that distance, slide it over, it falls on itself so that I can make the edges match when I paper my wall. Is there anybody in the room who's ever sewn? If you look at material, fabric has patterns that repeat. And if you're a very meticulous seamstress, when you look to make a garment, you want to make sure that at the seam, the seams, the pattern matches. So it's the idea that when I slide over a certain distance, patterns repeat. And now as I'm thinking of this idea, I'm in the spare room of my house. And does everybody have, well, I guess not everybody does. In my house, we've got this spare room where everything is dumped. It's a dumping ground. And as I look at across the room, another example of like wallpaper and fabric that has a repeat is gift wrap. And so I've got this left out yet roll of Christmas gift wrap. And if you look, as I slide down, the pattern repeats. And so it's got that idea of translational symmetry. As I unroll it, the pattern starts repeating. You see Santa occurs with the same elf in between him every time I unroll it. And so it's got that idea of translational symmetry where it repeats as I slide over. So is that enough of an example to wrap your minds around that idea of how something might have translational symmetry? Every time I slide, it repeats. So far, so good? Any questions? Can you guys hear me? Can you guys hear me?
Yeah.
Oh,
Yeah.
okay. All right, so translational symmetry, all right.
Yeah.
Okay, great. Then next place we're going to look. If this lets me move. Here we go. Is the idea of tiling. And if I tile a plane, I want to completely cover it. And when we look at tiles, we're going to look at our tiles as being different polygons. Has everybody ever stood in a room where there's, let's say, tiles on the floor, and you see different patterns of tiles, and those tiles fully cover the floor? And so we're looking at tiling a plane as completely covering the plane with no overlapping. So I'd like to pull up the virtual textbook and look at some examples of things that would be comparable to tiling. They have some lovely pictures in this section. So over here, sometimes you see something like a patchwork quilt. That's kind of like the idea of a tile. Sometimes you see, if I look at the one in the upper left-hand corner, each of those tiles per se is the same. The one next to it, the tiles are all very similar. But you see how I've completely covered the surface in each of these diagrams with the shape that I'm working with. And so when we tile the plane, we want to fully cover our surface with that shape. With me so far?
Yes.
Yeah.
And so the tiles can't overlap, and there's also no spaces between the tiles. And so when we first start looking at tiling the plane, we want to tile the plane with regular polygons. So before we start tiling the plane with regular polygons, can anybody refresh my memory on what it means to have a regular polygon? What does it mean for a polygon to be regular? Anybody remember what that definition means? Nobody remembers? A regular polygon is equilateral. And again, equilateral means all of the sides have the same lengths, and equiangular. All of the angles have the same measure. Can you remember with regular polygons, what we said with any polygon, the sum of the interior angles is 180 times n minus 2, where n is the number of sides. And if it's regular, each interior angle is that sum divided evenly by the number of angles. And we also said that each exterior angle is 360 divided by the number of angles. And so we want to take a minute and see which regular polygons can tile the plane. And so if I start looking at a triangle, can anybody remember what's the name for a triangle that's regular? What's the name for a triangle where all the sides are the same and all the angles are the same? Yep, equilateral triangle. And so I'm not a real good drawer, but if I have this equilateral triangle where all the sides are the same and all of the angles are the same, could I tile the plane with equilateral triangles? Could I draw equilateral triangles and have them cover my whole surface? What do you think? Does it look like that would be able to tile the entire paper if I wanted to? The answer would be yes. And the reason would be because if I have an equilateral triangle, does everybody remember the interior angles are 60 degrees? And so around any point, I could put these 60-degree angles, and all the way around that point, they would eventually add to 360 degrees. How about a quadrilateral, a four-sided figure? Can anybody remember the name for a regular quadrilateral, a four-sided figure where all the sides are the same and all the angles are the same?
Parallelogram.
Parallelogram, the opposite sides are parallel, but they don't all have to be the same length, and all the angles don't have to have the same measure. I'm looking for one where every single side is the same length and every single angle is the same measure.
A rectangle.
Rectangle, all the angles are 90 degrees. That's equiangular. We're getting closer. But in a general rectangle, do all of the sides, all four sides have to be the same?
Square.
Square. So a regular quadrilateral would be a square. And if I had squares, could I tile the plane with squares? Well, I think if you look at most tiled floors, you can tile the plane with squares because the interior angles, can anybody remember the measure of the interior angles of a square? How big are these angles in my square?
90.
90 degrees. And can I stack together those 90-degree angles? We'll place them next to each other. We have them add up to 360. Could I do that with a regular pentagon? Well, if I have a regular pentagon, it would have 5 equal sides, and it would have 5 equal angles. How big is each angle? If I take that 180 times 5 minus 2 and divide it by 5, what do I get? I'll give you guys a minute to do that arithmetic. Let me know when you have that measure. Has anybody found that measure for that?
I got 34.
You got what?
34.
Okay, tell me what you did.
I did 180 times 5 and then subtracted it by 2. And
Okay.
then divided that by 5.
Order of operations, we've got to take what's in parentheses first. So 5 minus 2 is 3. So we're going to take 180 times 3 and divide that by 5. 180 times 3, let's see, 3 times 0 is 0. 3 times 8 is 24. 3 times 1 is 3, and there 2 more is 540. And I've taken 540 divided by 4. Well, 500, I'm sorry, divided by 5, I apologize. 500 divided by 5 is 100. 40 divided by 5 is 8. So each of those would be 108 degrees. So one would be 108 degrees. The next one would be another 108 degrees. That would add up to what, 216. The next one would be another 108 degrees. That would add up to 324. Can I fit another one in here?
No.
But it's 324 isn't 360. So there's a space. So a pentagon cannot tile the plane. And I'm running out of room, so over here, let me write the word hexagon. And let's see, hexagon is 6 sides. Has anybody seen something like a restroom floor with those hexagonal tiles? Why does a hexagon work? If I look at a hexagon, what are the measures of each angle? If I take 180 times 6 minus 2 and divide it by 6, what would that give me?
$120.
120 degrees. And if this was 120 degrees, and this was 120 degrees, and this is 120 degrees, do you see how those angles add up to 360? And sometimes we call that the vertex angle. The vertex is the point where the tiles meet. And the sum of the vertex angles must be 360 degrees. And again, I have to apologize. As you look at my drawings through this chapter, I think you can see why I teach math and not art. So for a quick second, I want to pull up that virtual textbook. And on the next page, I believe it's the next page, you can see some pretty pictures of tiling with equilateral triangles, with squares, and with hexagons. And we can see that each of those will tile the plane quite nicely. Instead, if we look at, can I use pentagons? Well, because each of those angles were 108, 3 times 108 is too small, 4 times 108 is too big. So the answer there is no. And so to decide whether a regular polygon can tile a plane, we want to know if 360 is a multiple of those interior angles. So far, so good. If so, those are regular tilings where all of our tiles are the same size, regular polygons. We also talk about semi-regular tilings, and semi-regular tilings, we use different regular polygons. But each vertex figure has to have the same polygons in the same order. And so again, in order to be able to tile the plane, I'd have to have at each vertex the sum of the given angles must be 360 degrees. And even if we were on campus, this is a place where I would not try to draw these because I know I can't draw it accurately. And on the test, when you're asked if a certain combination of regular polygons could be a semi-regular tiling, could tile the plane, I'm not asking you to draw it. I'm asking you to look at those angle measures and see if they do indeed add up to 360. Does everybody have these words down so I can pull up the textbook and show you a pretty picture? Much prettier picture than I could draw. We good?
Yeah.
So again, going to that textbook, when they talk about semi-regular tiling, there's a couple of things that are important. And one is that the vertex figures have to be in the same order. And so they start with this diagram here, the blue and peach colored one. And you see how both of these at each vertex, I have 2 equilateral triangles and 2 regular hexagons. But these would not be the same tilings because they're in different orders. This first one goes hexagon, hexagon, triangle, triangle. And the next one goes triangle, hexagon, triangle, hexagon. So those would be different tilings. So far, so good. Now, they have this next page, some really colorful, nice looking tilings of semi-regular tilings. They've got here 8 semi-regular tilings. And so I'd like to expand one. And I don't know, there's 8 pictures there. Let's look at, oh, you know what, let's look at the one in the top right-hand corner. As I look at this one in the top right-hand corner, I'm trying to pick a color that pops. I'm going to look at any given vertex. And do you see how that vertex, what we've got here going around is a hexagon? Can you guys read that yellow or do I need a different color?
I can see it.
Okay, we've got a hexagon, we've got a square. We have a triangle. And then we have a square, right? So we're going hexagon, square, triangle, square. And at any corner, I can go hexagon, square, triangle, square. At any corner, I can go, let's pick one here, hexagon, square, triangle, square. So it's semi-regular, it's the same pattern all the way around. To see if that works as a vertex figure, the vertex figure again is hexagon, square, equilateral, triangle, square. We'd have to, and I'm going to recycle the numbers that we use. The hexagon we said was 120 degrees. The square we said was 90 degrees. The equilateral triangle we said was 60 degrees. The square we said was 90 degrees. And if I add those up, what does that total give me? $360 degrees, great. And so we know that that will work as a tiling because of the angles is 360. The sum of the angles, pardon me, is 360. So everybody all right with that idea of determining whether a sequence of regular polygons will tile the plane. The sum of each individual interior angle, one from each polygon, has to add to 360. Are we good with that? Any questions? Not hearing any, is it okay if I get out of the textbook?
Yes.
Okay, great. That, oops, I have to turn my finger back into a mouse. So we've got that idea of semi-regular tilings where they're regular polygons, the same ones at each vertex. And we know that at any given vertex, the sum of the angles has to be 360 degrees. So then next question that appears is, can any irregular polygons tile the plane? And what we're going to see is that any triangle, no, regular or not, can tile the plane. Because if I look at a triangle, I'm going to just pick a specific type of triangle. Let's say that that's a 30, 60, 90 triangle. Because of the sum of the angles is 180 degrees, I could rearrange that triangle so that the 90-degree angle is here, the 60-degree angle is here, the 30-degree angle is here, and then maybe I could put another one over here so that the 30-degree angle is there. And do you see, if I keep putting them so that at each vertex I've got one of each angle, and then I could repeat it so that at each vertex I have two of each angle. Because of the way the angles add up to 180, I would be able to tile the plane with any size of triangle. And the same would hold true with any quadrilateral, because if I look at an irregular four-sided figure, because I know the sum of the angles is 360 degrees, I could copy this figure so that, let's see, this angle would match here. I'm not gonna do a good job of drawing at it, but if I copy the figure so that at each vertex there's one of each angle, I should be able to tile the plane. And again, because I can't draw, I'm gonna again refer to a picture from the textbook if everybody's all right. So going back to that virtual textbook, we can see here an irregular triangle tiling the plane because I've got two of each angle at the vertex. And over here, do you see how I've got this irregular quadrilateral? And because I've got one of each angle at each corner, I know that those angles add up to 360 degrees. And so it would indeed tile the plane. So I ask that you remember that any triangle can tile the plane. I ask that you remember that any quadrilateral can tile the plane. The authors of the textbook go on and says, I can also tile the plane with any pentagon with parallel sides and any hexagon where the opposite sides are parallel. We're not going to go that deep down the rabbit hole. We're going to just say that any triangle can, any quadrilateral can. There's a couple other polygons that can, but the two that I ask you to remember are triangles and quadrilaterals. So far, so good.
Yes.
Okay, great. Then the last thing that we're going to look at is something that the authors of the textbook refer to as Escher-like tiling. I've also heard these referred to as tessellations. And a tessellation is where we create a tile that will cover the plane. And this is what I want you to have your index card, tape, and scissors with. We're going to do a little bit of arts and crafts now. When I've done this before with students, they've told me, oh, cool, that's something that I did in an art class. And they didn't realize that it was making use of this idea of translational geometry and angle sums and congruent segments and the like to tile the plane. Before we do this, is anybody familiar with M.C. Escher? M.C. Escher is an artist whose drawings have gone in and out of style. I know when my kids were like in middle school, his pictures kind of showed up everywhere. You see them at different places, different posters, things like that. Here's a copy of a Escher-like tiling where you can see that, and again, I'm back in the textbook. You can see that each of those tiles is that like unique bird shape, and they fit together perfectly. We can look at other drawings by him. But what we're going to do right now is we're not going to use a parallelogram, but rather we're going to use a rectangle to try to create our own tiles. And so if you look at, actually, you know what, rather than looking at this one, down here we've got one with those, with a hexagon where the pieces are slid across to create a tile that would cover the plane with this whale. I'm going to turn the page once more. Over here, here's a hexagon where you guys might have seen this with all the geckos, that kind of little lizards that kind of fit together. And they show how using rotational symmetry, we can create a tile that would do that. We're going to go down here and look at creating our own tile using an index card. And so if you see what they're telling you to do is to draw something on one side of the index card, cut it out, and then what we cut out on that one side, we're going to take and tape down to the other side. So what we cut out here, we're going to tape down at the opposite side. And then what we cut out on the other edge, we're going to tape to the opposite edge. And we're going to have a tile. We're going to look at it and see if we can see some sort of figure in it. And then we should be able to trace around that tile to completely cover the plane with it. Before we do this, a couple things that I want to point out from this homework. On dot paper, you're supposed to try to tile the plane with those different shapes. But question number 12, usually people aren't real successful with that one. We want to try to fit together C's. They can be right side up, upside down, left, right, backwards. We can spin them around to fit them together to cover a whole sheet of paper with C's, and the same with the F's, the T's, the H's, and the S's. You want to try to fit them together so that we can completely cover the plane with them and have no openings left. But let me go back. Let me stop sharing my screen. Let me see if I can set this up. And hopefully you guys will be following along with your own index cards with tape. I always love Tessellation Day because I think it's kind of fun. Can you guys see my hand in the paper down below, or is there a blue line in the way?
We can see.
Okay, so what we're gonna do is we're gonna take our index card. Oh, I should have a different color of paper underneath, not white, so that it actually shows up for a minute. So here we're improvising a little bit. I'm gonna take my index card, and on my index card, I'm going to, on one side, damn it, where did my scissors go? I made sure I brought up a pair of scissors with me today here. On one of the edges, I'm going to cut out a shape. It can be straight, it can be curved. I'm going to do a little bit of a zigzaggy thing that goes from corner to corner. And then I'm going to take that piece that I cut out, and I'm going to slide it to the opposite side and tape it. And here I think the stripes on the index cards help me make sure that I've got it lined up right so that I pulled it right across. Then I think I'm going to get a little fancy with mine. I'm going to, from this corner, cut a shape that goes not quite all the way to the edge. And I'm going to take this piece and slide it across and tape it directly across. Then I'm trying to be fancy. So from this other corner, I'm going to cut another one. And it looks like it didn't quite go all the way to the corner, so I'm going to try to make that little space at the edge. Match up with that little space at that tip. Try and slide it directly across. And so there is my irregular tile. And I have to apologize. I don't see anything looking at that. I don't see a fish. I don't see a butterfly. I don't see anything. The one in the textbook, I guess they were better at making random shapes than I, and they got something that they thought looked like a bunny rabbit. But I created this tile by cutting something out and taping it directly across. I do believe, I can't remember if it's a homework question or an activity that asks you to do something like this, but in that activity, they ask you to use a square, and what I cut out here, instead of going directly across, I spin it around and tape it on the other side. It's that same general idea. But now that I've got this tile made, I'm going to pick it up and I'm going to put it on my sheet of paper. I guess I'll start with edges at the edges. I should be able to, we'll start here. Trace around it. And as crazy as it is, the way I did it by translating those pieces that I cut out to the opposite side, I should be able to take this and slide it down like the pieces of a puzzle. and have it match exactly. And usually when I do this in class, I use slightly smaller index cards. I use perfectly square index cards. And I use slightly bigger sheets of paper where it's not an 8.5 by 11 sheet of paper, but rather it's a legal size sheet of twice the size sheet of paper. But you see how I should be able to trace around this thing and fully cover it. And if maybe I did a better idea of job of cutting my pieces out, I should be able to color them and decorate them and make an interesting pattern. And do you see how this sheet of paper, as I cover it, would be an example of that translational symmetry where as I slide, my patterns repeat. And so has anybody ever done something like this in something like an art class in elementary school or high school, where you've made these tiles by cutting things out and repeating them? I'm being met by total silence. Interesting? Something you might have kids do to get that idea of that the symmetries and the translations that you can do. And also if you start coloring them in and turning them into faces and the like, it's fun, yeah? So are you guys making your own tiles or no? Does anybody want to be brave and turn their camera on and show me your artwork? Is it working or not? I'm being met with silence. You guys, you don't know how much it scares me when nobody answers a question. I'm like, oh my God, are they still there? Are they listening? Or are they totally confused? Are you guys being quiet because you're engrossed with your cutting and pasting? Or are you, is everything okay?
Moving.
I'm sorry, I couldn't hear you. All right, I'm going to stop recording.